Hi everyone, this is the part 2 for galvanic cell. So, in this video, we are going to continue with the learning outcome G and the learning outcome J. Now, to begin with, I want you to open your tutorial book and find this list. You can find this list at the front of your tutorial book. But what is the use of this list? This list is known as standard reduction potential list. It is the measure of the ability of a half cell to attract electron towards it. This standard reduction potential is measured under standard condition, which is 1 molar, 25 degrees Celsius, and 1 atmosphere. How are we going to read the standard reduction potential list? At the reactant side, all elements are referring to the oxidizing agent, whereas at the product side, all are referring to the reducing agent. Let's take a look at fluorine gas. As we can see, fluorine gas is having the most positive SRP value. This makes fluorine gas is the best oxidizing agent ever, and it will undergo reduction. However, on the other side, fluoride is the worst reducing agent. And let's take a look at lithium. Lithium is having the most negative SRP value. This makes lithium as the best reducing agent, and it will undergo oxidation. On the other side, lithium ion is the worst oxidizing agent. How does the SRP value obtain? Now, this value obtained when the galvanic cell is set up between standard hydrogen electron and the other half cell system. Now, all the electrolyte must be 1.0 molar and the galvanic cell must be set up in 25 degrees Celsius with the pressure 1 atmosphere. This is the galvanic cell where we have standard hydrogen electrode and also another half cell which is copper. When we set up the galvanic cell, we measure the cell potential, which is here, by using the voltmeter, and to calculate the standard reduction potential for copper, we have to apply this formula. E naught cell equivalents to E naught cathode minus E naught anode. So our cell potential here, which is 0.34 volt, will be equivalent to the SRP for copper minus SRP for standard hydrogen electrode. The SRP value for standard hydrogen electrode is 0. Therefore, we can get the SRP value for copper, which is equivalent to positive 0.34 volt. And thus, you get the value SRP here. So what is SHE? SHE, also known as standard hydrogen electrode, and it is always used as a standard reference half cell. Why? Because the SRP or the E naught reduction for SHE is always defined as 0.00 volt. Therefore, you can see at the SRP list, it is 0.00 volt. So SHE is the best reference half cells to get the other SRP value for the other half cell. Now, standard hydrogen electrode consists of hydrogen gas that is bubbled at the pressure of 1 atm into 1.0 molar of hydrochloric acid at 25 degrees Celsius. And a platinum electrode is immersed in this HCl. The function of the platinum is to provide a surface on which the reaction can take place and serve as electrical conductor to the external circuit. He can act as anode and cathode, depends on the observation. Now, if you see there is no gas bubble produced, that means SHE acts as an anode and it undergoes oxidation to produce hydrogen ion. But if you see there's a colorless gas bubble produced, that means SHE acts as cathode. It will produce hydrogen gas, and that is why you can see the production of the gas bubble. Now, how to determine the anode and cathode from the questions? There are two ways to determine the anode and cathode. First, from the overall cell equation and cell notation. As you can see this from the previous video, we are given overall and we are given cell notation. From here, you know that this is anode. And this one will act as cathode. The second method to determine the anode and cathode is from the SRP value. Now, based on the SRP value, anode should be an element with more negative value, whereas cathode should be the element with the more positive value from the SRP list. Now, if you refer to the SRP list, you can see that going up to the list, it is getting more positive. Therefore, going up means it is easier to undergo reduction, and it usually they will become cathode. And then going down the list, which is the value, you can see the value is getting negative, it is easier for them to undergo oxidation. So usually they will be chosen as anode. Now let's take a look at this example. We have copper here with the SRP value positive 0.34 volt, and also zinc with the SRP value negative 0.76. Now, based on the SRP value, we know that the more positive value will have tendency to undergo reduction, and therefore they will be the cathode. In this case, the more positive value is copper. Therefore, copper will become the cathode. And in cathode, we know red cat. So in cathode, reduction will happen. So reduction, they always receive gaining electron. So we are going to write plus 2 electron to produce copper solid. And since copper become cathode, automatically zinc will become anode. Zinc will undergo oxidation. Therefore, we are going to write like this. Oops. Zinc to plus equals plus 2 electron. So that's how we know which one will be cathode and which one will be anode. Now, let's take a look at this question. Table below shows the standard electrode potential for various metals. So we have metal B, C, D, E, and F with their respective SRP value. Now the question is asking you to arrange the metal given above in order of increasing strength as reducing agent. Okay, now before we begin, let's take a look at this. This is written by using the cell notation method. Okay, so what I want you to understand, this one B plus here is the reactant and B is the product. So should we write like this? Produce B. And B, positive ion B to produce B means it undergoes reduction. Okay, so this is a reduction reaction, and then if you look at the standard reduction potential, like I mentioned before, all the equations here arranged in reduction way. Okay, now this question asking you to find the reducing agent. Okay, we are looking for reducing agent. So to look at the reducing agent, we are going to focus on the product side. Okay, they are the one that will become the reducing agent. Okay, if you look again at the SRP list, increasing strength as reducing agent increase when the SRP value become negative. The more negative the SRP value, the higher the tendency for the metal to become reducing agent. Okay, so how are we going to write this answer? The answer. Okay, so let's take a look at all the metals. We have B, we have C, we actually have D, E, and F as the reducing agent, and we are going to arrange them by referring to their SRP value. So the one with the most negative value will be the strongest reducing agent. So siapa? Okay, the answer will be E. So E will be the strongest reducing agent among all these 5 metals. So the strongest, okay, because we have to arrange them in increasing strength as reducing agent. So the second strongest will be C. The third will be D. The fourth will be B. And lastly, we have F. So we can say that F is the weakest reducing agent among all these 5 metals. So this is the first method to write your answer. Second method, you can also write like this: F, B, D, C, and E. Put an arrow here and write increasing order of strength as reducing agent. Okay, madam minta maaf ya, so madam punya tulisan sangat tak cantik. Okay, so this is how you find the answer. Alright. Okay, now let's take a look at these questions. So if the previous question asks you to find, to arrange the order of increasing strength as reducing agent, now this question asks you to arrange in ascending order of their oxidizing strength. Okay, oxidizing strength, which means they have a tendency to become oxidizing agent. So to become an oxidizing agent, Like I told you before, we are going to focus on this part. Okay, we are going to focus on this part because the reactant part will be the oxidizing agent. Okay, now to be an oxidizing agent, okay, we are going to look at the value and it should be more positive. Okay, more positive. Should be. Okay, sorry, we shouldn't write like this. This is not the list, but we have to arrange, right? So let's see. Okay, if we want to rank them, the most positive is F2. Okay, so we can write F2. Okay, the second positive is Cl2, then followed by Br2, and lastly is iodine. Okay, it is iodine. So we also can arrange them. I2, Br2, Cl2, and F2. Okay, if you are using comma, you have to write the arrow, okay? So here, you can write ascending order of oxidizing strength. Okay, to make it easy, you can just write down this. Okay, write them back. All right, there you go. Okay, so for the third example, okay, you are given two half cells, which is tandem and zinc, and then the half cells are connected by a salt bridge. Now write the half equation at the anode, cathode, and the overall cell equation. Okay, so let's see, we have tandem and zinc. This is their SRP. Okay, so we know cathode should be more positive and anode should be more negative. Okay, so which one is more positive? Okay, anode should be more negative, right? More smaller. So our anode should be zinc. Okay, because it is more negative compared to tandem. So we know at anode it undergoes oxidation. Therefore, we are going to write zinc okay, plus 2 electron, and then at cathode. Okay, of course, tandem will undergo reduction because it is more positive, not electropositive, okay, more positive. So we are going to write tandem to plus aqueous plus 2 electron to produce tandem solid. So our overall, this one and this one will cancel each other, and we are going to get this. Okay, there you go. Okay, so we have our half cell for anode, our half cell for cathode, and our overall cell. I hope by looking at these three examples, you now understand how to determine anode, how to determine the cathode by looking at the SRP value. Now, how to calculate the standard cell potential. Previously, I had shown you how to calculate the standard reduction potential value for copper. We are using the formula E naught cell, which is equivalent to E naught cathode minus E naught anode. E naught cell is also known as standard cell potential. Okay, standard cell potential. or also known as standard cell voltage and standard electromotive force or EMF. Now, when using this, I want to give you some tips. Okay, ini tips dari Madam. Now, sometimes, okay, we were given value and we want to know which one should be cathode and which one should be anode. Yes, of course, previously I told you it must be, cathode should be more positive and anode should be more negative. Okay, there's another way for you all right? Okay, usually I will tell my students E naught cat minus E naught anode. Okay, cara mudah untuk mengingat, cathode is K, A, anode is A. K is for kakak. Okay, K is for kakak. A is for adik. So, kakak mesti sentiasa lebih besar daripada adik. Okay, kakak mesti sentiasa lebih besar daripada adik. Sebab tu, kakak mesti lebih, value cathode mesti lebih besar berbanding value anode. Kakak mesti besar daripada adik. Okay, guys, this is tips from Madam Carol. Okay, ini tips untuk mengingat sahaja. Iklan sekejap ya. Okay guys, now let's take a look at the next example. Write the cell notation for the reaction below and calculate the standard cell potential. So we have here chlorine and fluorine. For us to calculate the standard cell potential, we need to identify our cathode and we need to identify our anode. Okay, we have two questions here. We need to write the cell notation and also calculate the standard cell potential. So, first thing we have to do, identify the anode and identify the cathode. So if you follow the tips that I give you before, which is anode should be smaller. Anode is adik, right? Adik mesti kecil. So if you look at these two SRP value, we can see that the smaller value will be chlorine. And therefore, chlorine will be anode and undergoes oxidation. So we are going to write 2Cl minus producing Cl2 gas plus 2E. Whereas at cathode is kakak. Cathode kakak kan? Kakak mesti besar. So the one with the big or the more positive SRP value is fluorine. So fluorine will undergo reduction. Okay. So this is it. We have this and we have this one. Next, to write the cell notation, don't forget the method ABC. But no need for you to write the the stoichiometry. So we just write Cl aqueous separate, Cl2 gas bridge. Now fluorine gas separate, and then F minus. Therefore, this is our cell notation. Okay. Now, to calculate the E naught cell, we know we want to get E naught cathode minus E naught anode. Kakak tolak adik. Kakak mesti besar. Kakak tolak adik. So just write positive 2.87 volt minus positive 1.36 volt. Tum-tam, tum-tam, tum-tam. We are going to get 1.51 volt. There you go. Easy, right? Okay, let's take a look at this second example. An electrochemical cell is made by connecting a zinc electrode immersed in zinc sulfate solution and an aluminium electrode immersed in aluminium nitrate solution. By referring to the standard reduction potential table, write the half cell reaction at each electrode and the overall cell reaction. And then B, you need to write the cell notation. And then C, you need to calculate the standard cell potential. So let's focus on A first. Okay, so you are given here the SRP for zinc and aluminium. Identify which one will be anode and which one will be cathode. So we know anode, it must be the elements with more negative SRP value or smaller SRP value. So if you look at this, we can see, if you compare, we can see that actually the aluminium is having more negative SRP value. Therefore, aluminium will become the anode. So what will happen? Aluminium solid produce aluminium 3 plus aqueous plus 3 electron. Then our cathode will automatically be zinc. Okay, so we're done with A. Oh, sorry, no, we haven't done with A yet. We need to write the overall equation. So as you can see, our number of mole for electron is not the same. Therefore, we need to make them same by multiplying this with 2. And this part we are going to multiply with 3. So we are going to get 2Al solid plus 3 zinc 2 plus aqueous producing 2 aluminium ion plus 3 zinc solid. So this is our overall. We need to write overall. Okay, we need to write like that. So we are done with A. Let's proceed with B. Now, B, we need to write the cell notations. So we know to write the cell notation, we need A, B, C. So our anode here is aluminium. Aluminium, solid, separate, aluminium ion. Okay, no need to, no need to put the stoichiometry. Bridge, and then B, C, cathode. So zinc 2 plus aqueous, separate, zinc, solid. There you go. So this is our cell notation. And lastly, C. Calculate the standard cell potential, which is E naught cat minus E naught anode. Okay, fun fact everyone. As you can see at the beginning, we have to multiply anode with 2 and we have to multiply cathode with 3. So what will happen to the SRP value? Are we going to multiply them too? The answer is no. You no need to multiply them like in thermochemistry. Okay? Please remember, thermochemistry is different. In electrochemistry, no matter how many times you multiply it, the SRP value will remain unchanged. And therefore, since our cathode here is zinc, it would be negative. We are going to get negative 0.76 volt minus negative 1.66 volt. So, tum-tum, tum-tum, tum-tum. Wow, much we are going to get? We are going to get we are going to get, we are going to get 0.9. Okay, positive 0.9 volt. Ding. All right, there you go. Again, please remember, no matter how many times you multiply the anode and the cathode, the SRP value remain unchanged no matter how many times you multiply the half cell. Ding, ding, ding. We are done. For your homework, try to do the tutorial question from question 1b, question 2, and question 3. Sometimes, the question will ask you whether the reaction is a spontaneous or non-spontaneous. So what is the meaning by spontaneous or non-spontaneous reaction? When you calculate the cell potential or standard cell potential, we will say that the reaction is spontaneous when your standard cell potential is positive, okay? When your standard cell potential is positive. And we will call the redox reaction as a non-spontaneous when the standard cell potential is negative. But if you get your cell potential equivalence to 0, therefore the reaction is at equilibrium. So how do we know whether it is spontaneous or non-spontaneous? Let's take a look at the next questions. Okay, you are given a reaction, copper and ferrum. Okay, so how do we know whether this reaction is spontaneous or not? Okay, let's take a look. First thing, you have to identify which one is anode and which one is cathode. Okay, take note that this time you cannot look at the SRP because you are already given a reaction. Okay, you are given a reaction. So from the reaction, you have to identify which one is anode and which one is cathode. So how do we know which one is anode and which one is cathode? We have to look at the oxidation number. So if you look at this, from 2 plus, it becomes plus, which means copper undergoes reduction. So reduction, red cat, reduction happened at cathode. Therefore, we know copper undergoes reduction. So again, we have to write this according to the overall equation given to you. Okay. Now, if you look at ferrum, okay, from 2 plus, it becomes 3 plus. The oxidation number is increasing, which means it undergoes oxidation. So ferrum 2 plus produce ferrum 3 plus electron. Okay, now how do we know whether it is spontaneous or not? We have to calculate this. Okay, we know our cathode is copper. Copper is positive 0.15 volt minus, and for anode we have positive 0.77, positive 0.77 volt. So what will we get? If you calculate, we are going to get negative 0.62 volt. Now, see, you have negative answer. So when you get negative answer, we know that this is a non-spontaneous reaction. Okay, so this reaction actually cannot happen. Okay, it actually cannot happen, but you can make it happen by using electrolytic cell, by applying or providing electric to the redox reaction. Okay, but again, this is how we determine whether it is non-spontaneous or spontaneous. Now, let's take a look at B. All right, so let's do the same way. First thing, we identify what is our anode and what is our cathode. So let's take a look at aluminium. Okay, as you can see, from 3 plus it becomes 0. The oxidation number decrease means it undergoes reduction. So reduction happened at cathode, red cat. So we are going to have aluminium 3 plus 3 electron producing aluminium solid. Okay, and then at anode, our calcium will undergoes oxidation. Yeah, if you look at here also, you can see that the what we call this, the oxidation number is increasing. So we have this 2 plus 2e. So why they become 2 and why they become 3? Because this one you multiply with 3 and this one you multiply with 2. Okay, but we don't need the overall equation here. We need to determine whether it is spontaneous or not. So E naught cell, E naught cat minus E naught anode. So our cathode here, aluminium, is negative 1.66 volt minus our anode here is calcium, which is negative 2.87 volt. So we are going to get positive 1.21 volt. Jing, jing, jing. We have positive here. So since this is positive, therefore this redox reaction is a spontaneous redox reaction. There you go. Okay. Now let's take a look at the final answer. This one might be a little bit confusing, but worry not, everyone. So actually, ferrum 2 plus will produce two things, which is this one and this one. So as you can see, the top one here, the oxidation number is decreasing, which means this one undergoes reduction. But for the below one here, from 2 plus become 3 plus, this one undergoes oxidation. So let's write the equation first. Okay, we have anode and we have cathode. I love to write cathode first because I always remember the red cathode, okay? Reduction at cathode. So we have ferrum 2 plus, okay, plus 2 electron to produce ferrum solid. Okay, let's write the E naught cell for cathode, which is negative 0.44 volt. Okay, then we proceed with anode. Okay, we have Fe2 plus as well, but this time it produces ferrum 3 plus 1 electron with the E dot equivalence to positive 0.77 volt. Now this one is actually you have to times with 2 to balance the electron at cathode. However, the SRP value will remain unchanged, okay? Please remember that. Now, let's proceed. Okay, so E naught cathode, our cathode here is negative 0.44 volt minus our anode here, which is positive 0.77 volt. Okay, so what are we going to get here? We are going to get 1.21 volt, negative 1.21 volt. Okay, so as we can see, we are getting negative answer here. So we can conclude that this redox reaction is a non-spontaneous reaction. Am I right? Ta-ding! Yes, we are correct. So I hope that all this example will help you to understand how to determine the spontaneous and non-spontaneous redox reaction. For your homework, for the spontaneous and non-spontaneous, please do the question 4 from the tutorial book. And last but not least, the grand homework for everyone is the question 8 from tutorial book. Try your best to do these questions, okay? So thank you guys, and I'll see you in the next class.